Synthesis of Clostrienose. Clostrienose is a complex polyketide produced by this anaerobic bacterium here, and they're important in promoting cellular differentiation processes. The bacterium itself is well known for its historical use in producing organic solvents such as acetone. I've also provided the article link in RSC format. So I will be going through 3 reactions today, the first being a halogenation where we're forming a C-Br bond, the second being a variant of the Stele coupling reaction where we're forming a C-C bond, and the third being a protection of a cis-diol using acetonide and we're forming 2 new CO bonds. Please note that the bonds formed in reactions 1 and 3 don't actually contribute to the final skeleton of Clostrienose, and I've just highlighted the areas where this reaction occurred. So the first reaction is a halogenation, more specifically an electrophilic bromination of this terminal alkyne here. We're using NBS as our source of bromine, a silver catalyst, and acetone as our solvent. So in the first step, we are using our silver catalyst to activate the CC triple bond. It can do this because silver has a D10 electronic configuration, which favors interactions with the CC pi bond of alkyne. This is also known as alkynophilicity. This will facilitate the deprotonation at the terminal carbon of the alkyne because this carbon is sp hybridized, and so it makes the hydrogen more acidic. Upon removal, we form nitric acid as well as this acetylide anion, where the silver has a strong affinity for the very nucleophilic carbon. Formation of the silver acetylide ensures that the carbon is a better nucleophile for when it undergoes electrophilic bromination by NBS. Silver has Lewis acid properties, which can activate NBS by coordinating to the carbonyl oxygen and withdrawing electron density, which will make this NBr bond more polar, and this will facilitate the bromine transfer to the alkyne. The pi electrons of the alkyne bond will attack the polarized bromine, thereby forming our product with the new C-Br bond. We also end up making the silver salt of succinimide, which then gets protonated by the nitric acid that was formed when we made the alkynyl silver species. And then we end up making succinimide as a byproduct, as well as regenerating our silver catalyst. The next reaction is a Magita-Kosugi-Stele coupling reaction where we're using a palladium dimer catalyst. Although the palladium is already at an activated oxidation state of 0, it's possible that ligand dissociation can occur to form a single palladium catalyst with the oxidation state unchanged. For simplicity, I'll be referring to the catalyst as PDLN. So we first start with the association of this palladium catalyst, which has an oxidation state of 0, which is in its activated form, with this substituted allyl system. Instead of the typical halide leaving group, we have this carbonate leaving group at an allylic position, which makes this compound act as an allylic electrophile. We end up forming this palladium pi complex, where the oxidation state of the palladium remains unchanged. It will then undergo oxidative addition, forming these 2 palladium eta 3 pi allyl intermediates in equilibrium. Note that the oxidation state of palladium has changed from 0 to 2. This system will then undergo transmetallation because we have an organostanane partnered with our halide ion that's provided by lithium chloride. This is needed because the carbonate leaving group is a poor ligand for bonding to tin. The carbon-tin bond breaks and we end up transferring this organic group to the palladium center of the pi allyl complex. This can now undergo reductive elimination where the organic group or the vinyl group acts as a nucleophile to attack the less substituted carbon, which is here, to form this cross-coupled product with a new CC bond, as well as regenerating our palladium catalyst, which has changed back from an oxidation state of 2 to an oxidation state of 0. So the last reaction is a protection of a cis-diol using an acetyl group that's provided by DMP. PTSOH is our acid catalyst, and we use acetone as our solvent. So first, DMP gets protonated as one of the methoxy groups' oxygen will donate its lone pair of electrons to the H+, that's provided by our acid catalyst. It then undergoes elimination where the other methoxy oxygen will form a carbonyl bond, allowing the methanol group to be released. This carbonyl-carbon is now more reactive, allowing one of the OH groups from the cis diol to attack this delta negative carbon, creating this hemiacetyl tetrahedral intermediate. An intramolecular proton transfer will then occur, forming another methanol leaving group, as the oxygen will form a carbonyl bond. The oxygen from the remaining diol attacks the delta negative carbonyl-carbon, forming the 5-membered acetonide ring. We also regenerate our acid catalyst by deprotonation. This reaction is stereospecifically syn, as the acetonide can only form with the diol in a cis position. Thank you for watching.